Welcome back, everyone, to day 4 of the second week of the summer school. Today, as yesterday, we'll have 2 lectures, one in the morning, one just after lunch.
No, we have like we will have 3 tutorials and only one
Okay,
lecture.
so we'll have
today.
one lecture and 3 detailed tutorials today, so which is a different kind of learning opportunity, I think.
Yeah, so we have, so they needed, so there will be one extra tutorial compared to what was planned earlier and one less lecture. So, sorry,
Please take it away.
Okay, good morning, everyone. So let me start with what we were doing towards the end of yesterday's lecture. So if you remember, we were trying to relate the properties of the halo, in particular its mass, to some properties which we can use to calculate a gravitational wave observable. So in particular, we ended up with something which looked like this. So we said that the number of merger per unit time, per unit chirp mass, per unit redshift range, per unit halo mass, this would be and then the time delay distribution times psi, which we said will be a function of m and z. So this is the star formation rate. And then this uncertain quantity, which is the merger rate happening in halo of mass m, where the halo has formed at redshift zf and the merger is happening at redshift z, per unit chirp mass range, per unit stellar mass, times the halo mass function. So from here we can compute 2 quantities. One is, suppose you are just interested in the total merger rate you observed per unit time, per unit. So this will be just this quantity, and you integrate over all halo mass. So I'm not writing this quantity again. And we also said that it is possible to calculate the clustering properties of gravitational wave events. So that will be something like dm b m of z, and then again this whole quantity. So to do all this, firstly you need a model for star formation rate, which you may be able to do, because if you have a model for star formation rate, most likely you will be able to relate it to the luminosity of galaxies. And since we have observations of luminosity function of galaxies now till reasonably high redshifts, you probably will be able to control this to a large extent. But then you need to go from star formation to like gravitational wave event formation. And that will involve calculating this quantity as well as trying to find some idea about how much time will it take. These relations are, of course, written under like many simplifying assumptions. And let us talk a bit about them. So firstly, you may first say that these merger events may be occurring, but the resulting amplitude may not be detectable in the detector. Okay? So you may need to put some kind of this, what we talked about earlier, some selection function based on SNR. So assuming you are able to calculate the amplitude of this signal and you know your detector sensitivity, you will be able to calculate SNR. So you have to put some cutoff that not all these events will be observed here. So SNR above some value or amplitude above some amplitude are only observable. So you can include a corresponding selection function in the calculation. Then we assumed one galaxy per halo. It may be much more complicated than that. This we know at low redshifts. At high redshifts, maybe things were simpler. The galaxy formation was kind of less evolved. But nevertheless, if the data demands, you may need to go to something which is more complicated than this. Then, of course, we assumed things like psi, which depends only on M and Z. Similarly, DN merge only depends on M. But they may have other dependencies. For example, they may depend on the metallicity, which is also related to the stellar IMF. And there could be other properties of the galaxy as well. And on top of that, there could be scatter in these relations. In the sense, even when the halo mass, metallicity, and all other conditions are very similar, there could be some difference in this value, some stochasticity or some history of the halo. We have also assumed, the star formation rate is at ZF. Should be careful. We have also assumed that the star formation rate is given at ZF. ZF is the redshift at which the halo formed. So the halo formed at redshift 13. So you calculate the star formation rate as redshift 13 and that is it. Okay. And then you say after that, I will add some delay time to form the merger. But it is possible that this is also extended. In the sense, it can depend on the age of the halo. So the halo forms at redshift 13, but star formation rate might be going on for 1 billion years after that. So then just like you have a time integral here, there will be another time integral which you have to put. And then, so suppose the halo forms at redshift 13, so star formation starts and it goes on till lower redshifts. And then from every star formation redshift, it's possible that some stars are going into like eventual binary merger event. So then from every of those redshift, you have to wait till the delay time and work this out. So basically one more integral here. Then what we haven't accounted for is halo mergers. Halo once formed may not be just like survive throughout the age of the universe. In particular, they, as we were discussing yesterday, they can merge and form a larger halo. Now imagine that this process was going on. So one can ask that if the merger happens, what will happen to that process? So it's not very easy to answer. It's not it's not that they will completely get disrupted and it will stop. Okay, it depends on how the merger happens, how the halo merger happened and where was this binary event sitting in that galaxy. So it may or may not get disrupted. But what can happen is if the halo merges, so initially you were forming something in a halo of, let us say, 10 to the 9 solar mass, then it got merged and became a halo of, let us say, 3 into 10 to the 9 solar mass. That may change the correlation structure. Okay, so now you have to associate that event to some other halo mass and the corresponding bias may get affected. Okay, so all these things will create complications in the calculation. Of course, one can also take the approach that we are probably far away from reaching a state where we will have enough observations to do all these statistics. And in tomorrow's lecture, I will give you some idea about these projections people have made. So as of now, probably simple models are enough. So you just try to see with simple models whether we are there to, we are in a place to even detect the signal. All these complications can come, but it is good to know what are the things which are involved and what are the things we can learn when these observations are here. Okay. Yeah. Halos are forming at, even at redshift 1, halos are forming. Halos are forming throughout, yeah.
Like detection as a binary, or it would be like a gravitational wave?
No, here I'm talking about individual event, number of mergers per unit time. So yeah, I'm talking about individual events. Why? Because I need their redshift. And if I want to do correlation, I did not write the correlation function, I wrote the bias. I need some idea about the position, individual positions, okay? I'm not talking about stochastic, so I won't talk about the stochastic part here. Okay, so this is really to do cosmology with the correlation function.
Just trying to understand what are the number of such a binary events can happen in such a way.
Yes, so firstly we want to understand what is the number, and then if possible I want to also calculate the two-point correlation function of those events. So for that I need to have some idea about, okay, I will have some idea about the redshift from most likely from the luminosity distance measurement, but I want to also have some idea about the localization, where they are. Okay, and how these localization errors spoil sport, I will show some results in tomorrow's lecture. Okay, we did some calculations on this. Okay. Beyond this, there are various other effects which you may have to account for. One thing which is known as magnification bias. I forgot to ask, did Surhud talk about lensing in his lectures? He avoided lensing, okay, fine. So I will do, I won't derive the equations, but I will quickly tell you what this magnification bias is. So essentially what happens is, you people have heard this thing, lensing, right? So what happens is, as the light from a high redshift event is streaming towards us, it gets deflected by the gravitational potential of the intervening sources. So depending on how massive the sources are, this deflection will be high. But in general, even if the deflections are not high, they can statistically build up because of all this matter present between that galaxy and us. And this lensing can affect your calculation of, for example, clustering, okay, which we are interested in. So there are various effects of lensing. Two effects which are often used are magnification and shear. So magnification is basically, from the name it is obvious, the flux of the source becomes brighter than what it would have been without the lensing. So lensing basically converges the light rays in such a way that the object appears bright. Shear is what basically distorts the shape. Okay, so it basically it is a distortion. Shear is a relatively weaker effect than magnification. That does not mean it is less important, because shear is something people use in lensing surveys to do cosmology. But in our case, what I will talk about is magnification. So because of magnification, two things happen. Okay, so now because of magnification, what will happen is, suppose you are observing a set of sources, the magnification and your detector or your telescope will have some flux limit. You won't be able to observe sources fainter than that limit. Because of magnification, what will happen is, some of these fainter sources will now enter into your detection threshold. Okay, so in gravitational wave events, this will be characterized by SNR. They will cross the SNR threshold in galaxies, they will talk about the whatever magnitude limit or something equivalent. So this may lead to observing more number of sources than otherwise. So if you see more number of sources, what will happen is, imagine just like we had written delta halo, I can write something like delta galaxy or delta gravitational wave event. So that will be like number of gravitational event divided by mean number of gravitational event minus 1. Okay. Now what will happen is, since now you are observing more sources, this quantity may go up than what you would have otherwise expected. However, there is another effect. Okay, so what happens is, in lensing, something called surface brightness is conserved. So magnification is accompanied by increase in the solid angle. So that basically reduces number of sources per unit area, per unit solid or per unit solid angle. And that is the thing, if you remember when we are doing projected densities, that is the quantity we are interested in. So now if the surface increases, your number density kind of goes down. If the solid angle increases, this thing goes down. So there is these competing effects. Which one will win will depend on various factors. For example, how many faint sources you have. Just to take an extreme example, suppose your survey is super, that it observes all the sources. Okay, so then you don't gain anything because of the magnification, the increase in flux, right? Because anyway you are observing all the sources. But you will lose because of the area. Okay. And similarly vice versa. Suppose your observations are at that limit where if you just reduce, if you improve the your survey sensitivity a little bit, many sources will come into your detection limit. Then basically that will lead to increase in the number of sources you see, and hence delta. So again, as I said, since I'm not going to do the calculations, I'm just giving you. So delta, I'm just writing G. I mean, it could be GW also, gravitational wave also. People write this under some assumptions that this is 5s minus 2 times kappa, where kappa is the convergence field. So I'm again not writing the whole thing. There is a kernel which depend on depends on Z source and Z, and this one will go from 0 to Z source and times delta M. So this is basically what is known as lensing convergence. And S is the slope of the what you call the luminosity function. Basically number of sources at your detection limit, and how the slope, I mean how the derivative of that quantity, what is the value of the derivative at that quantity basically. So let me just write it. It is the logarithmic slope of number counts. So what is happening is, if you are so imagine the source is at redshift ZS, then the lensing will be contributed by everything between 0 and ZS, and the corresponding matter density will appear here. And this is a kernel which depends only on the geometry, like what is the difference between the co-moving distance between the lens and the source, and so on. So this is a complicated factor, but it's a known factor, and that is what appears here. So this is how the observed density changes. Now you see, now if you do calculate the power spectrum, what will happen is, or correlation function, you will do a delta G, right? Delta G observed, delta G observed. And that will involve the true delta G. But it will also involve, so you will multiply this with this itself and take the average. So it will also involve a delta G times kappa, and kappa will involve a delta M. So there will be a delta G delta M term with all sorts of integrals and other things put in. So I'm again giving you the basic. And then there is a kappa term which will essentially involve delta M. But there are like integrals, so delta M's can come from two different redshifts as well. So basically your observed correlation is kind of modified by all these effects which show up. Okay, and in principle, while doing this, you should account for that. This effect is relatively less prominent at large scales, but they become extremely important at small scales. Again, this is a qualitative statement, so you have to really do at least some quick calculation to see how it affects your, the correlation function you are interested in. There is another effect, which is basically smoothing of the power spectrum. What happens is, because of lensing, the positions of the sources, the angular position of the sources are kind of changing because they have moved away. And because of that, there will be a smoothing in the power spectrum. And that will depend on how strong the lensing is. All these things can in principle be calculated, and one needs to then see. And this smoothing will again smooth out the power at small scales. This is similar to, again, there will be, I think, a problem done, and also probably you will do in the simulation, that if you like miscalculate the position of the galaxies or the halos in the case of simulation, what happens to the power spectrum. So depending on how much error you make, you will see around those scales, the power kind of starts to decrease, get suppressed. That was about lensing. Okay, so I'm not going into more details than here, because otherwise one would have to go through this whole derivation. So in the rest of the today's lecture, what I wanted to do is a bit of kind of other effects, talk about some other effects which can play important role in trying to measure these correlation functions. So the next which I want to talk about are peculiar velocities. Till now, while doing the linear perturbation theory, we did talk about velocities, but after that, when we were doing correlation function and other things, I never mentioned velocities. So what happens is, peculiar velocities will basically affect your clustering measurement. Now, how do they do that? So essentially what happens is, suppose you want to measure the distance along, so suppose you want to do correlation function. You want to measure distance along the transverse direction, that is basically on the plane of the sky. So to do that, you will measure the difference between the angles, the angular separation between them, and then convert it into a distance using, for example, angular diameter distance at that redshift. Okay, so these distance measures, I'm sure all of you have done. This is transverse. Along the line of sight, for galaxies, you will measure the redshifts. And that redshifts you will convert into distance. And this you will do using the Hubble parameter at that redshift. Now, but when you measure redshift, the assumption here is this whole redshift is coming due to the underlying Hubble expansion of the universe. But in reality, there will be peculiar velocities. On top of Hubble expansion, things may move closer to us or away from us relative to Hubble expansion. And because of that, you will make an error in calculating the distance between the distance along the line of sight between two galaxies. And if you make an error, that will show up in your correlation function. So the true correlation function will now get modified because of this effect. So this is known as redshift space distortion. And I will do some quick calculation to show what happens because of this. Now, what is interesting is, suppose you are able to measure the distance without taking help of redshift, then this effect is not going to play a role. So suppose you measure distances directly through DLZ, as you may be able to do in the gravitational wave events, then this redshift space distortion will not play a role there. You may be hit by the uncertainties you have in measuring the luminosity distance, but that is a separate question. However, now if for the gravitational wave events, if you go and observe the host galaxy and calculate their redshift and use that to do your cosmology, then again you have to worry about peculiar velocities. So just keep this in mind. It is not like every observation or every survey in the universe will have redshift space distortion. Particularly for gravitational wave cosmology, this is something you should keep in mind. Nevertheless, let me talk about redshift space distortion and see what happens. So just to write some equations, so what you will do is, suppose you observe some galaxy. So if the galaxy had only cosmological redshift, then this would have been the relation between redshift and the distance to that galaxy. So ZCOS is the cosmological redshift. So this is assuming there are no peculiar velocities. But on top of that, there is something arising from peculiar velocities, and that redshift I can write as 1 plus some VR by C, 1 minus VR by C minus 1, where VR is the velocity along the line of sight. So transverse velocity doesn't make any difference. It's the line of sight velocity which is a problem. And what you will observe is a combination of these. So in case of small redshifts and non-relativistic velocities, what will happen is that Z observed will be given by, if you just do these calculations, you will see that it is H naught R by C plus VR by C. So H naught R by C is your standard Hubble-Lemaitre law, and on top of that you have this VR sitting. This is for our nearby universe and also when the velocities are small. See, what will happen is, what is in your hand, what you will observe is only this quantity. What you are interested in this is the true distance, but it is now modified by V, and there is no way of like separately estimating the V. What can happen is, if you have an independent measurement of R, you can do the V. So for example, if you have a measurement of the DL, and also you see the host galaxy, so you measure its redshift. Then you can use this, assuming some cosmology, you can use this to calculate what would be the peculiar velocity of that galaxy. But otherwise, when we do galaxy surveys, this is not possible. Unless, near very close by galaxies, there are ways to calculate distances from various relations, empirical relations. But for most of cosmology, this is not possible. So given this, then we have to include this effect in our calculations. There is no other way. So to do that, what you do is, so first, let us see. So in absence of peculiar velocity, I could have assigned a distance, saying that the distance is this, okay, when there is no peculiar velocity. So you take the observation and so in the absence of peculiar velocity, what you could have done is you would have said that the distance is c times z by h naught. Okay. So let us say I just use the same relation for the observed redshift. So clearly S is not the true distance anymore. Okay, it's the true distance plus the effect of peculiar velocity. In fact, we can write it. So this will become r plus VR by h naught. So this quantity is called redshift distance. And this is true distance. True distance, real distance, whatever. And just so that we don't get confused, currently we are working in terms of physical or proper coordinates. I will go to co-moving again very soon. You can write this in a vector notation as well. So you say S vector is R vector plus the velocity along the R direction divided by H naught. So the distance is modulated only along the line of sight, and the component of the velocity which plays a role is also the one along the line of sight. If we go to high rate shifts, then you have to just generalize this. So this becomes R plus V dot R by H of A R. You could have written H of Z also, but what happens is in some of these calculations, people take the line of sight direction as Z sometimes. So there could be some confusion there with redshift and the Z direction. So fine, let's call the time as A. We'll put back redshift whenever is needed. Okay. So remember, so this is the true or real distance, or that is the redshift distance. Redshift distance is the only thing we kind of observe. So now let us try to see first, like qualitatively, what is the effect. So one thing it's clear from there as well, that S is greater than R when VR is greater than 0 and vice versa, right? So if the peculiar velocity is away from us, then you will infer a larger distance. Whereas if the peculiar velocity is towards us, you will infer a smaller distance than the real one. So one way of seeing what happens is to use, for example, our spherical collapse. So imagine at very early times, so it is expanding with the universe, but there are, because it is overdense, this shell is falling, but overall it is still expanding. Okay, it hasn't turned around. Now in this case, so this is real space. It is a sphere. In redshift space, what will happen is, for example, these 2 points will remain where they are. Okay, so imagine this to be your reference redshift. So these 2 points are not going to change. At least the relative distance between these 2 points are not going to change because they are only in the transverse direction. This point will seem closer to us, and this point will seem further from us because the velocity here is positive. So in redshift space, it will look something like this. Okay, yeah, this is the observer. Yeah, there's no space, so the observer is here. Okay, yes. Correct. We always look upwards. Now imagine it has turned around, but still, sorry, yeah, it has turned around. So now it's a competition between the Hubble velocity and the peculiar velocity. What will happen is at some point it will pick up so much velocity that so it has started to probably collapse, okay, and it has picked up sufficient velocity that this one, for example, almost compensates for the Hubble. Then what you will see is almost fully squashed thing. Okay, it's basically come and almost fell on top of each other. Now beyond this, what can happen is a crossover. So this velocity has become more than the Hubble velocity. So as a result, things which are otherwise nearer to us would seem further and vice versa. So what will happen is there will be a flipping of this. At the final stage, what can happen is your spherical shell has collapsed and it has picked up huge velocities in all sorts of directions. Okay, but mostly, I mean, it's quite random basically. In that case, what can happen is this flipping can become very extreme. So what you can end up with is something which looks like this. I mean, this is not correct because the transverse size will be whatever I drew here. Okay. So, I mean, the way I'm drawing it's probably not good. Remember, this sizes are equal, though they don't look equal here. Because the transverse size, nothing changes. So in this case, the transverse size will be something like this, and there will be. And remember here, this corresponds to this point, and this corresponds to this point. And this will be like really huge velocities where you have gone beyond Hubble. So this clearly, this is something which will happen at large scales when the system was large. And at small scales, this is the kind of effect you will see qualitatively.
What happened?
So at the end, what will happen is you will virialize the system and it will pick up huge velocities. The velocities will be given by the potential, Gm by R. And those velocities can easily exceed the Hubble, the velocity corresponding to the Hubble. Okay, so it will be completely on the other side. And it is also not systemic, basically, like here, where everything was smooth. It's quite random. But what we understand is once the velocities become larger than Hubble, the flipping is almost inevitable. This, I mean, all these effects are seen in observations, in either statistically or in real. This one would look like structures are all, so this is where the observer is sitting. What will happen is no matter which direction you look, it will seem like the structures are elongated towards you. So if you are sitting here, you will see structures which are like looking like this. Okay, it's pointing towards you. I did not prepare slides today, otherwise I could have shown something from a galaxy survey. This is known as finger of God effect. Okay, it's as if somebody is pointing fingers towards you in this cosmic sky. Finger of God effect again is a small scale effect. It's very important and it has been observed. But since we are interested in relatively large scale like correlation functions, I will mostly focus on the first part. The advantage also in focusing on the first part is we are assuming at large scales and the things are probably still expanding, not too much collapse has happened. So some ideas about linear theory can still go through. Okay, that is the advantage of doing at large scales. So what we can do is, let me again write S equal to R plus Vz by H naught A times Z. What I have replaced in that equation is I have replaced R, where is my equation, R by Z. So what happened was, if you are sitting here looking in all directions, depending on which directions you are looking in, the peculiar velocity will play a role along that direction. So that is why I put R. But most of the time, the perturbation scales we are interested in, the correlation function scales we are interested in, are much smaller than the distance to that. So correlation scales you are interested in will be what, 10 megaparsec, 20, maybe at most 70, 80, 100 megaparsec. Okay. But for example, if you calculate co-moving distances, even up redshift 0.25 will give you 1 gigaparsec of co-moving distance. And if you are looking at higher redshifts, you are really looking at large distances. So what we did is we said that let us just work in the plane parallel sky approximation. So just imagine that we are looking here and this is our Z direction. So this just simplifies the problem. Okay. So we have assumed plane parallel sky basically. So now what will happen is, I mean, imagine this shell and within this shell there were galaxies sitting. All these galaxies will now in the redshift space will sit in this shell, okay, or this volume. So now if I treat this as a coordinate transformation between S and R, where R is the real coordinate and S is this coordinate, I can use conservation of the number density or density. So if I am observing, let us say, galaxies, and I put a superscript S saying that this density is in the redshift space, in S space. S d cube S should be equal to rho galaxy real space, so I am not putting anything here, and d cube R. So now rho galaxy in redshift space will be rho galaxy in real space modulated by the Jacobian of R and S. And that Jacobian I can calculate because I have written the relation between R and S. So again, I am not doing the full calculation, but if I mean, there are few steps here. If I make linear approximation, so whenever I say linear approximation means I will ignore higher order in deltas. What we will end up is, I mean, what we will do is we will write this in terms of delta and then make the linear approximation. What you will get is delta galaxy S in the redshift space will be delta galaxy real space minus 1 by HA, which is sitting, oh, there's no H naught A, this is HA, del VZ, del, I mean, I'm calling it RZ, meaning basically the position along the Z direction. Okay, I mean, at Cartesian coordinate you would have called del Z, but then we will get confused with redshift here. This del Vz, del Rz comes because we will take derivatives while calculating the Jacobian. Okay, so this is where it will come from. And now let us shift to co-moving coordinates. So this will become delta galaxy at some position x minus 1 by a times HA del Vz del xz, the z component of the co-moving coordinate. So this is how the overdensity will change. And this is the kind of formula we often, I mean, even during lensing, we wrote something similar, like what you observe is the true plus or minus something else coming from other effects. It is easier to work in Fourier space as usual. So you go to Fourier space. So this I can just remove to be consistent. In Fourier space, delta GS of K would be given by delta galaxy of K. So this derivative will be replaced by an appropriate factor. So that will be IK AHA times VZ of K. The solution of the linear theory will tell you that this quantity is nothing but I kz by k square times delta m of k. Times HAAF. Okay, so this whole quantity is this. So let me just explain. What will happen is you can relate this velocity, peculiar velocities, to the underlying matter density using continuity equation or a combination of continuity Euler or Poisson equation. You may have to do some manipulation. You write them in the Fourier space, you will get there. And then you have to also put in the evolution part. And if you go back and see, the velocity evolves as a times d dot. And then we replace d dot by a quantity which we call f. F is just the logarithmic derivative of d with respect to log a. Okay, so again, these will be in your notes if you have taken. And this, for a given cosmology, this can be calculated. Okay, so for example, a good approximation is omega m to the power 4 by 7 of z. Now, what I can do is, you can see this delta m, I can replace by bias of galaxies times delta of galaxies and do some manipulation. Some of these HA and A factors cancel out. And what you at the end get is delta galaxy of K times 1 plus beta kz square by k square, where beta is nothing but Fa by bias of galaxy. Okay. Just constantly shifting between G and GAL. So whatever you want to use, be consistent. So this quantity basically characterizes how much distortion you will have because of peculiar velocities, and you see depends on basically the direction. Okay, so depends on the k will now, I mean, k is actually your kx, ky, kz. And kx and ky is not playing any role, but what value of kz you choose will be affecting your delta galaxy observed. Okay. So if your kx, ky, so suppose you take now the same k, but I mean the same k will, as I said, the k is basically given by kx square plus ky square plus kz square. You choose a combination where kz equal to 0 and kx and ky they combine to give you some k. In that case, delta gsk will be delta gk because kz is 0. You choose another kx, ky, kz combination which has the same k, but now kz is non-zero. As a result, kx, ky is smaller than earlier. And that will give you something else. So you will see now there is a difference between what is happening in the transverse direction and what is happening in the line of sight direction. And that is what that was. Okay. Now this essentially tells you that even if the universe is, let us say, isotropic, as a result the underlying power spectrum we showed is a function of mod k only. But because of peculiar velocities, now that is not true anymore. What happens is the power spectrum now becomes different in the sky plane and different in the along the line of sight, even if the underlying power spectrum is isotropic. So what we can do is we can write the corresponding power spectrum. So it will be B galaxy, the real k, times 1 plus beta, and let's write in terms of mu k square, where mu k is nothing but kz by k. So basically, I mean, it's basically what we call the cos theta, where theta is the angle between k and the z direction, line of sight direction. Call it. And I have to put a square. So now it has become a function of theta as well. Okay, it is not just a function of modulus of k. If it has become function of theta, what you can do is you can expand in terms of Legendre polynomials. If it had become a function of both theta and phi, we would have expanded it in terms of spherical harmonics, which I indicated how to do, where things depend on both theta and phi. Since this is still phi symmetric, only theta, so you can leave out this e to the ik phi terms in the I phi terms in the spherical harmonics and work only with Legendre polynomials. So what you will do is you will take this power spectrum observed and expand like L equal to 0 to infinity the power spectrum for various orders times the Legendre polynomial, which is a function of mu. So this is the Legendre polynomial. And if somebody gives you can calculate all these coefficients by doing appropriate integrals. So I will write down some of the first few coefficients. For example, P0 S of k will be the underlying k times 1 plus 2 by third beta plus 1 by fifth 5 beta square. And P1, sorry, it's only the even components which will come. So you will see that it is PGK times 4 by 3 beta. And so on, okay, in principle. So first three components is what people do. But what I'm trying to say is, yeah, suppose, so this is observable, right? This is observed. What you can do is from observations, you can calculate this from observations. You have to just either expand it and then look at appropriate powers of mu or do appropriate integrals. But once you have, so we will treat it as these quantities which are kind of observed. But now if I observe all these quantities, suppose I take a ratio of this underlying power spectrum gets cancelled out, I can calculate the value of beta. So beta is something which can be calculated from observations. Okay, so you get the value of beta. And beta is f of a by bias. Now suppose I wrote this as bias of galaxies, but I can do it for different kinds of galaxies. And if I do it at the same redshift, even if I don't get the actual value of the bias, I can get the relative value of the bias. So I can at least tell you which galaxies are more biased than others. Okay? Though I may not be able to tell you the exact nature of the bias. But then what you can also do is, once you have calculated the value of beta, you can put this back and get P galaxy of K. And once you have gotten P galaxy of K, the true one now, that will give you bias. In fact, what will happen is that will give you bias times some sigma 8. You won't get the full bias. Okay. So this is often used to get handle on the value of FA, and FA has information about the growth factor. So peculiar velocities can help you calculate the growth factor from observations. Okay. So that is often, this kind of numbers are taken and used, and then people, because the growth factor depends on Hubble parameter and hence the cosmological parameters, you can do cosmology with this. So now the other thing you see is this one, P0K, is what is known as the spherically average power spectrum. Spherically average power spectrum is that you take the observed power spectrum and integrate over all angles and divide by the total solid angle. So that is the spherically average power spectrum. And what would happen is, if there was no redshift space distortion, the spherically average power spectrum would be the true power spectrum. And if there was no beta, all the higher order terms would be 0. Okay, so this is what we expect. But now that you have beta, firstly you see the spherically average power spectrum is larger than the underlying power spectrum. This has happened because you have increased the density in overdense region. So what has happened is you have shrunk this part. Transverse direction was same, but you have shrunk the volume along the line of sight direction. And whatever was inside remains inside. So effectively, overdense regions became more overdense. And similarly for underdense regions, the opposite thing will happen. Things will be moving away because they are expanding. So this volume will increase. So as a result, your fluctuations increase and the power spectrum increases. So that is the effect of redshift space distortion. Now just to make the point, these may not be present in the actual the observations where you measure the actual distance. But often people will be talking about, for example, taking gravitational wave surveys and cross-correlating with galaxies. So there you need to be very careful. So for the galaxy surveys, you should include the redshift space distortion effect. But for the gravitational wave events, you should not. Okay. So appropriate powers of that quantity should be included in the calculations. This goes by the name Kaiser effect. This is true in the linear regime and hence at large scales. In principle, this Kaiser effect will show up in your simulations as well, but then you have to do some work to take into account the velocities and then appropriately move particles in the redshift space. Now, there is this interesting thing which happens, that the isotropy of the power spectrum breaks down because of peculiar velocities. There is another effect which also breaks down the anisotropy, the isotropy of the power spectrum, and introduces anisotropy along the line of sight. So let us try to understand how that happens. So suppose I give you, let us say, 4 galaxies. So there is some center, and let us say there are 4 galaxies. Okay, all are at same distance from this. Okay, so this is some delta x, this is also some delta x. Delta x and delta x. You can even assume a spherical shell if you want. So these have the same co-moving distance, let us say. Okay. But observationally, I'm not going to measure the co-moving distance. What I'm going to measure is the delta theta along the plane of the sky, and then convert it into delta x. Along the redshift direction, along the line of sight direction, I will measure delta z and convert it into delta x. And to do that, I have to assume a cosmological model. Why? Because here I will need the angular diameter distance, here I will need the Hubble parameter, and these are given in terms of h naught and omega m and omega lambda and whatever is in your cosmological model. Now suppose you choose a wrong cosmological model. Then what will happen is, even though your delta x's are same, you convert it into, what you will measure is the delta theta, and when you convert it into delta x, if you assume the wrong cosmological model, the delta x along the transverse direction and the delta x along the line of sight directions won't be the same, because you are using different quantities in cosmology, different geometrical quantities to calculate that. Okay. This is known as geometrical effect in general, or sometimes people call this Alcock-Paczynski effect. Alcock, this is more difficult. Okay, AP. So this will also, what it will do is, even if you have isotropic distribution, if you choose wrong cosmological model, it will make it anisotropic, and what it will do is, it will treat the line of sight direction different from the sky plane. So the anisotropy introduced will be qualitatively similar to the redshift space distortion. So there is some kind of degeneracy between this geometric effect and the redshift space distortion. In cosmology, ideally, if you want to really check this effect, what you need is something where you know that the delta x's are same. Okay. See, if I give you a galaxy distribution, you don't know a priori whether it is isotropic or not, because you will infer these delta x's and then look at them, and if you have made a mistake, then anyway that is gone. But suppose you know intrinsically that there is something which is same along any direction you look at. What we are looking for is a standard ruler. Okay, so you know the size of that ruler, and then that you can use to check for this AP effect. And that usually comes from what is known as BAO, the baryon acoustic oscillations. So these oscillations you see in the CMB, angular power spectra, these are happening because of interaction between baryons and photons. And this imprints, this gets imprinted on the underlying matter power spectrum. And even when the universe evolves, this imprint is there. So in the correlation function of matter, it shows up as a bump, okay, at a particular scale. So this scale is of the order of 150 co-moving megaparsec. And this in principle can be used to do this Alcock-Paczynski effect. But otherwise, yeah, this can introduce something which looks like RSD. But now you see, so now suppose you have a set of observations where the redshift space distortion is not there. And suppose you know that you expect a power spectrum which is isotropic, then your calculation, suppose you assume a cosmological model and find the power spectrum and find that it is anisotropic, then you are almost sure that it is happening because you have chosen a wrong cosmological model. So this can be a very good test of cosmology, because now you say I want to find that cosmological model which makes the power spectrum isotropic, and that will be the true cosmological model. So that is again something which is worth exploring in the gravitational wave cosmology as well, because as I am constantly highlighting, this other degeneracy is not there. There could be other effects due to lensing, because lensing also affects things along the line of sight, but those effects are they show up at somewhat different scales. Yeah. And finally, so today we may be able to finish a bit early. I just wanted to talk a bit about BAO, because that is so important in cosmology. So as I was saying, the BAO essentially shows up as a peak in the correlation function, and hence as some kind of wiggles in the power spectrum. So there is a lot of effort to basically measure this feature in the galaxy power spectrum and power spectra of any tracer you talk about. And many of the recent results you have seen would have come from BAO. So this has become extremely important. What is usually done is, the advantage of this feature is, suppose you are trying to look only for the location and not the amplitude, because you are looking for a standard ruler and you will use that to do cosmology, then it is somewhat easier than other probes, in the sense what you say is, I have something which is smooth and on top of that there is a bump. So I will try to fit my observable with something which looks like this, a smooth component and on top of that a small bump. And I will just try to find the location of that bump. And that is what is done. And this is done not using both galaxy surveys as well as Lyman alpha forest. Okay, we did not talk about Lyman alpha forest at all, but that is another very important cosmological probe, and both can be used to do BAO. People now are really trying to do BAO with various other upcoming probes, more galaxy surveys. So these galaxy surveys are basically based on the luminosity, some star formation, the UV luminosity of the galaxies. But people are thinking of trying to use, for example, neutral hydrogen inside galaxies to do similar surveys. And the hope is that with that, we will have independent probes, and who knows if there is any systematics here, if that affects your H0 tension, then that will be worth seeing. So again, the initial hope was, again, tomorrow I will show some results. The initial hope was that with gravitational waves also, one may be able to do something like this. But because if the localization errors are huge, then what happens is there is a big chance that that feature may get washed out. So then it will be very difficult to detect it. Okay. So I think I don't want to start the next thing. So yeah, so let me just stop here today. So we have saved some time in today's lecture. So tomorrow what I will try to give you is a flavor of what kind of research is being, some examples of what research is being done in gravitational wave cosmology, particularly using this two-point correlation function and power spectra, and how are people planning to use them to do various things. So this of course will happen in the future, but people are already doing calculations. And also tomorrow I will talk a bit about how in high redshift universe and how gravitational waves can be very useful in studying the very early times in the universe in the future. So these are the two things I will talk about tomorrow. But today, let me stop here. Yes. Another peak. Okay. I have to see what you are talking about. So this is a peak which is coming at 150 megaparsec. If you have looked at power spectrum, there will be multiple peaks. So one peak will show up, I mean, sharp feature will show up as a wiggle in the power spectrum. So if you had noticed the power spectrum plot I showed in the first one, it would have had that small wiggles. So it depends now on whether you looked at correlation function or power spectrum. But yeah, just show me, then I will remember what we are talking about. Yes.
So how do you know that it is not an ellipsoid collapse or something like that? Like it would be like some road.
I don't know, right? It is all combined. So you observe what you observe. Okay. So
you have to do the component analysis.
okay. So are you talking about lensing or the redshift space distortion? Redshift space distortion, it is easy, no? So what I'm saying is redshift space distortion at large scales shows up in a very particular form, this Kaiser form. Okay, so what I can, okay, ideally if I had a very perfect measurements across all angles, then I could have just gone and seen whether it fits this. That is difficult. So what people do is people expand in terms of Legendre polynomials and calculate the first 2-3 components, and that is possible. And then you go back and see whether that matches with what you expect, and indeed it does. So that is the good part. I wrote everything in terms of power spectrum, but similar relations exist in two-point correlation function as well. And then you can plot the two-point correlation function and clearly see. So again, I did not prepare slides, but I could show you plots where people see these structures in the power spectrum very clearly. Both finger of God effect. So in small scales, it will look something like this, and at large scales it will look something like this. Okay, equivalent of these. So that is seen as a function of scale in the galaxy correlation function. Yes, that is finger of, no, I mean, right. So for, okay. So firstly, finger of God effect is at much smaller scale. So one would probably be more worried about differentiating between Kaiser and this one. It is not very easy. So you have to basically do a full like parameter estimation and see what happens. Okay, but I don't think the geometric effects show up like having this kind of shape. So that helps in breaking something. But yeah, there is a bit of degeneracy. On the other hand, yeah, we think that we know cosmological parameters to a large extent from CMB. So that helps a lot. But yeah. So in BAO calculations, this AP effect is always, I mean, you have to take into account. But there the advantage is to a large extent that since you are interested only in the location of the peak and you can do a bit of reconstruction of the linear part, what happens is this can be taken care of quite easily. So you can make the underlying power spectrum isotropic because here you know that in both the directions, the feature should appear at the same place. Okay, so that helps in breaking, I mean, looking for AP effect. So there you have removed the peculiar velocity effect. So that is why BAO are very useful in doing. So that is why nowadays, I mean, a lot of cosmological parameter estimation are done using the BAO rather than the full power spectrum. Yeah. So here I would say the main advantage is to measure the beta and through that either bias or this growth factor. So those are useful things as far as peculiar velocities are concerned. Observationally, okay, at high redshifts, we cannot measure peculiar velocities individually. You just get the total redshift. At low redshifts, again, I don't have a quantitative number, but in the nearby universe, for example, in the local universe, we have like velocity maps. So what they do there is basically from the continuity equation, you can relate the peculiar, there is a relation between peculiar velocity and the underlying density field. So what you can do is you can characterize the underlying density field and through that you can draw arrows of the peculiar velocity field. And that is very reasonably well done in the local universe. And for low redshifts, yeah, you can probably do this where you have a very good handle on the densities, density field, I mean, independent of redshift. So you measure the density field in terms of like real positions, you know the positions of the galaxies through some other method. And then from there you can calculate the velocity field. But at high redshift, this becomes difficult because we don't have an independent way of measuring the distance.
If we have no more questions, let's thank Tirthankar.